Good morning to everyone. It's nice to see you after yesterday's dinner. I see that not everyone died. Okay, so yeah, I will talk about this fast test of the impact of marginalization in Monte Carlo analysis and its application to cosmology. This is a presentation that is based on this paper of mine that appeared last year in September. It was published in Phys.Rev.D. And yeah, I'm going to first of all introduce, I guess that most of you know what is a marginalized posterior, but I would like to review explicitly this concept, which of course plays a fundamental role in Bayesian analysis. I will explain that when we have non-Gaussian features in the original posterior distribution, we can obtain bias results. Okay, so this is important to bear in mind. And I will illustrate this with a very simple two-dimensional example. I mean, with an example in a parameter space composed only by two parameters. And then I will motivate the use of the so-called profile distribution in order to mitigate these problems. Okay. With the profile distribution, we have one important problem, is that the computation is very expensive, very time-consuming, if we want to obtain the profile distribution for all the parameters of our theory or model. And this is why I thought about this method that allows you to estimate the profile distributions in a very fast way and directly from the Monte Carlo Markov chains with no additional investment of computational time. Okay? And I will show you the results when this method is applied for the standard ΛCDM model, the ultralight, axion-light hybrid energy model, who was very nicely discussed yesterday by Vivian, and coupled with this and Brans-Dicke model with cosmological cluster. And then I will end up as usual with the conclusions. So why do we need Monte Carlo analysis? So you know that the posterior distribution plays a central role in the Bayesian analysis, and this is basically given by the prior of the by the product of the likelihood and the prior, with this p appearing in the denominator being a normalization factor, which is called the evidence. And of course, if we want to obtain constraints in our parameters of the theory or the model, we have to know very well which is the shape of this object. Okay. I'm not saying nothing new here. The problem, of course, is that we need to the first thing that could come to our minds is to build a grid in parameter space and then evaluate the posterior at each node of the grid. Okay, we could do that, but the problem is that the number of evaluations that we require in order to draw this posterior is extremely large if we are dealing in parameter spaces of 20 or 30 dimensions. This is the basic problem with the grid method. No? And this is the case, for instance, if we perform a CMD analysis with the ΛCDM model. So it's completely unfeasible to learn the shape of the posterior using the grid method. So this is why we use, of course, Monte Carlo sampling, because the same analysis can be done with only 10 to the 5, 10 to the 6 evaluations. So we reduce by a large number the number of steps that we have to perform to know this information. And the preliminary output that we get from a Monte Carlo analysis is, of course, the Monte Carlo Markov chain. Okay. So, in principle, we have all the statistical information of interest contained in the Markov chain. Now, if we are dealing with into 20, 30 dimensions, it's impossible to get directly. How can we interpret this? No? We have to reduce the dimensionality of the object that we are analyzing. And this is done usually applying the marginalization method. This is how we reduce to 1 and 2 dimensions, and then we can visualize the results and then interpret them This is very trivial. I know that most of you know that, but I want to make the introduction in a very detailed way. So, what is marginalization? Basically, we have a parameter space composed by θ1 and θ2, where θ1 is a subset of parameters and θ2 is another subset of parameters of our theory or model. And we want to obtain the posterior distribution associated with θ1. We just have to perform an integral over θ2. So basically, we have to sum the values of p at a fixed θ1 for all the θ2. Okay. In particular, if θ1 has dimension 1 or dimension 2, we get the one-dimensional marginalized posterior distributions and the 2D contour plots. So the truth is that performing applying the marginalization method is quite trivial, let's say. If we have a Monte Carlo Markov chain, we can make a grid for the parameter of interest and then count the number of points in the Markov chain that fall inside each pin of the grid and use this information to make a histogram. Okay. Of course, if the Markov chain is sufficiently large, then we will achieve convergence. But marginalization does not concern, in general, the statistical information content. And it's very easy to understand why. Imagine that we have a large value of this object, the marginalized posterior, at a given value θ1 star. Do we know why? We cannot know why using only this value. Right? It could be that we have a very large peak of the original posterior in a very small region of the parameter space, or we can have a low value of p in a very large volume of parameter space, right? And if we want to estimate tensions, this is important. This is very important. So the take-home message from this slide is that there can be points in parameter space that are able to fit very well the data, but have a very small marginalized posterior due to volume effects. Okay? So this is why some people, even the people from Planck in 2013, use the profile distribution and analyze how the constraints change. Okay, the profile distribution is very defined by this simple relation. Okay, you just have to take the maximum of the posterior for a given value θ1, and it has some advantages. The maximum of the one-dimensional profile distribution is located exactly at the same location that maximizes the original posterior. So there is no shift, basically, in the bits. The profile distributions are not subject to volume effects, obviously. We are not performing an integral. And these objects, the profile distributions, lead to more robust constraints, especially when the original posterior has important non-Gaussian features. When we are dealing with an exactly Gaussian distribution, the profile distribution and the marginalized posterior coincide. Okay? But there might be differences if non-Gaussianities are important. So just to illustrate this problem in a very simple way, imagine that we have a two-parameter model. Let's call them alpha and beta. Okay, and we have two experiments. Experiment 1, okay, which is which gives us this posterior distribution. Okay, basically, this is the sum of two Gaussian, but you know the sum of two Gaussians are not Gaussian. And I plotted here this distribution coming from experiment 1, and of course we can make the projection in the 2D plane of alpha and beta, and we get this kind of Pinocchio shape. Okay, and you see that the region, the 68%, the 1 sigma region, goes up to here, more or less. Okay, due to this additional probability here. We have two peaks. Very good. And then we have a second experiment which is only able to constrain alpha. This is given by this Gaussian constraint, which I have plotted here. And you can see that the two experiments are perfectly consistent. Well, there is no tension here. There is no tension. It is compatible. The two experiments are compatible at 1 sigma. And this implies that we can use both of them to extract a constraint. and we get this very small contour. Okay, but normally we are not dealing with two parameters. We are dealing with 20, 30 parameters depending on the number of nuisance parameters that our theory has, no? And as I mentioned before, we have to reduce the dimensionality of the problem to 2 dimensions for 1 dimension. So here we could be already biasing our results because we are applying marginalization. Now, this example, in this example what I've made is, okay, let's analyze what is the tension when we analyze the marginalized posterior in 1D. Okay, so if this can be computed analytically, basically. So the posterior distribution for alpha is given by this curve. Okay. And here, this blue region is the 1 sigma, 2 sigma, and 3 sigma region. Okay, obtained from the 1-dimensional marginalized posterior. And then I compare this probability with the one coming from experiment 2, which is a pure Gaussian. What we obtain is that we have a 3 sigma tension, which was not present here. Right? This is only due to volume effects, nothing else. And here we are dealing with 2 dimensions going to 1 dimension. Imagine that we have no Gaussianities in 30 dimensions, and then we reduce the dimensionality to 2 dimensions. Something crazy could go on. We do not have a good control of what's happening. Okay, so if we apply the profile distribution, okay, so this is what I know is very basic, but the 1 sigma region coming from the profile distribution is given by these vertical lines in black. And you can see that experiment 2 and experiment 1 are perfectly compatible with the sigma, which is what we would expect. So this means that using the profile distribution could make a difference. So some remarks that I want to make at this point is that in a 2-dimensional parameter space, as I mentioned before, it is very easy to study the existence of tensions, but in normal applications in cosmology, we are dealing with much higher dimensional parameter spaces. So working with the profile distributions would be important. The problem becomes more involved, as I mentioned before, in these high-dimensional spaces. We don't need to go to a modified gravity with I don't know how many parameters. Just take an ЛCDM and Planck data. Now, of course, it has some advantages, as I've mentioned, but the computation of the exact profile distributions in high-dimensional parameter spaces is very expensive. Why? Because we have to minimize the posterior. We have to perform this maximization of the posterior for every value of the parameter. We have to bin our parameter space and then perform a minimization in each bin. And if we want to repeat this process for all the parameters of our theory, this is unfeasible. This is why I suggest the following. So, if you would apply a profile distribution method, first of all, you need to know what are the prior range that you need to explore, right? Because if you want to perform a bin of your parameter space, you need to know where the profile distribution will be 0 or very close to 0 in order to put some bounds, no? So you need to perform a preliminary Monte Carlo Markov chain analysis. And the question is, can we take advantage of this preliminary Markov chain analysis to somehow estimate the profile distribution directly from the Markov chains without any extra minimization process? The answer is yes. So this is how we, the method that needs to be applied if we want to estimate the one-dimensional PDs from the Markov chains. So we need to build a grid for the parameter of interest, and in each node search for the maximum value of the posterior and just save it. So you don't need to remove the baryon phase or whatever. The larger the amount of points, the better, actually. So you basically apply this formula and then you plot the result and compute the confidence intervals. This is basically what I've done in the 2-dimensional, in the example in 2 dimensions that I showed in the previous slide. So, as I mentioned before as well, the estimation of the PVs with this method does not require additional computational time. So let me show you what are the results in some cosmological models. So I've made use of this data, Planck 2018, temperature, polarization, and lensing, the Pantheon compilation of supernovae type 1a, and video data from different galaxy surveys. So these are the results obtained with the ΛCDM model. Okay, I performed this test as a benchmark test just to make sure that the method was behaving well. Notice that Planck collaboration performed the exact profile distribution analysis in 2014, and they obtained that the results from marginalization and the profile distribution are essentially the same. There is no important difference. Why? Because here non-Gaussian features are not important. Okay, there are no important non-Gaussian features in the main cosmological parameters. No? And with my method, I've reproduced the results. So you see that the shifts in the values of the parameters are not significant at all. But what happens if we want to analyze irregular energy? And this was already mentioned by Vivian yesterday. In this analysis by Hero et al., they applied the exact profile distribution method to just one parameter. Of course, they could not analyze the complete parameter space because, as I mentioned before, it's super expensive from the computational point of view. So they analyzed the maximum fraction of irregular energy using the profile distribution and the marginalization method, and they found very significant differences, even using this very basic data set that I was telling you about, without including large scale structure data and so on. Okay? So basically, I have been able to reproduce with this very fast method their results. Okay? So notice that when we apply the marginalization method, using no data from shoes, for instance, they do not obtain any peak in the profile, marginalized profile distribution. Okay, there is no evidence for irregular energy. But if we apply the profile distribution, a peak at 2.3 sigma appears. No use of shoes data here. We are not forcing anything. We're just using the profile distribution with BAO, supernovae, and CMB. But my method is quite fast, so I could explore the complete parameter space of the theory. And not only so, also the nuisance parameters and derived parameters of interest. But I'm showing here some of the main parameters. So you see that, as expected, a shift in the value of the irregular energy fraction is also translated into shifts on other important parameters. For instance, the absolute magnitude of supernovae type 1a. Okay. The value of the sun horizon at the baryon Drake, the value of NX. Omega B is not that much affected, but other parameters as omega CDM also is very affected by this issue. And of course, H0. And I want to, so this what I'm going to tell you now is, what I'm going to tell you now is somehow disconnected a little bit from the main topic, but I wanted to insist on this point. Are we sure that the use of sigma 8 is correct? I mean, we are using the Roomian square of mass fluctuations at h divided, at 8 divided by h megaparsecs. This means that if we want to compare the results from the ΛCDM and irregular energy, and we compare the two values of sigma 8, these two values, it makes no sense to compare these two values. Why? Because the scale at which we are evaluating the amplitude of the power spectrum is completely different. If the value of H0 is shifted, we are producing shifts in the value of sigma 8, which are unnatural. We are comparing the power spectrum at two different scales. So we might be introducing additional tension, or maybe we are reducing the tension in an unnatural way. So this is why, Ariel Sanchez in 2020 propose the use of an alternative large-scale structure estimator, which is very similar to sigma 8, but it's evaluated at a fixed scale, which is not affected by age, at 12 megaparsecs. If you use this, then you can compare the amplitude of the power spectrum at the same scale, regardless of the model that you have, and regardless of the posterior for each node that you have coming from the different models. And this is interesting. Okay, I'm again analyzing hybrid alternative. This, okay, of course, when you apply my method, you obtain somehow noisy results, so it's difficult to build the 2D contour plots using the profile distribution coming from the Markov chains, but you can analyze correlations. Okay, so I'm 2 minutes. Okay, so you can analyze correlations, and this is the relation that you obtain. The more the larger is the EV fraction, the larger is S8. Yes, the larger is FEV, the larger is each node, the larger is FEV, the largest is omega CDM. Why? Because you need to suppress the integrated Sarsgaard effect. The same positive correlation is obtained for NS, but there is also something important. There is a positive correlation between FEV and the cosmological constant. Okay, and this is important. Why? Because omega m can be kept at very similar values in the ΛCDM, and it's omega m and not this quantity, which enters the equation of the matter density contrast. Okay, if we are able to keep omega m constant, the amplitude of the power spectrum will not change that much. And this is what we observe here. There is no correlation at all between FEV and sigma 12. Okay. So I don't see any worsening of the large scale structure tension in the context of FEV. Okay, I will not analyze what happens in coupled quintessence, but basically I do not obtain important shifts in the coupling strength or the Phys.Rev.D parameter. Also in Brans-Dicke, things seem to be stable. But yeah, I finish now. So maybe I can skip. I can say that we have applied the method to 4 interesting cosmological models. We have been able to recover the expected results for the ΛCDM. So this is fine because Planck already found that in 2013 with previous data release. We find the important that volume effects play an important role in hybrid energy. Okay, and in contrast to other previous analysis in the literature, we have been able to provide full profile distribution constraints of the theory. This has been done for the first time in the literature. Okay, yeah, that's it. Sorry for. Yeah, in general, you expect some.
Right. So you showed us like maybe an ED model where basically all my non-Gaussian distribution become Gaussian, and.
Sorry, can you repeat?
Everything became, all your distribution became Gaussian after you did ED. Right? Everything was beautifully Gaussian. It was close to Gaussian, right?
Yeah. Let's. Yeah, it's. Well, notice that there are some important deviations from some parameters. No? Imagine, look at R. Okay, you mean when you go to the profile distribution?
Exactly.
Okay.
Everything is skewed, and then it goes to the red cells look like Gaussians, right? Or it's close to a Gaussian.
Yeah, not exactly, but yeah, I agree that.
Right. But if you're in a regime where you expect non-Gaussianities in the distribution, what's going on here? And how do you know that you're going to get Gaussian or not? Like you go to your couple of contestants, for example, right? You put it forward and get a clear slides. Okay, this is after the PD. Okay.
Yeah, well, for this parameter, there is some deviation from functionality.
When do you know when to apply this and when not to apply this?
Exactly. This is the point. So, in general, if you want to compare profile results coming from the profile distribution and marginalized posterior, you need to invest a lot of computational time. No, if you want to do that for all the model, the parameters that enter the model. This method allows you to, perform a Monte Carlo as in the standard analysis, and then you can compute both and just see. Of course, my method has some noise. This is not exact, but it allows you to estimate the impact of non-Gaussian features in the original posterior. This is why this method is interesting. Okay, if you find very important non-Gaussianities, then it's not worth to apply the exact profile distribution. Now, in ULA, in this irreducibility model, there are important deviations. Okay, so now you can think about applying the full machinery and see the exact results if you want.
So if I did high Z data, so I showed you an MCOT yesterday, right, where
yes.
it's very skewed, there's nothing, there's volume, there's projection effects.
Yeah, so in this case, it's important, it could be useful to apply this method. Yeah.
Okay, another question more, please?
Yeah, one thing that bugs me about this is that there's no criterion to decide whether marginalization or PD or one is better than the other. I mean, they're both just approximations.
Yeah,
they're both just losing information.
I think that we cannot say, okay, we cannot say that if we want to estimate or assess the level of tension,
right.
I would prefer to use profile distribution because I know that they will work always.
Well, but what does work mean? You know, they're both losing information, and so if they're giving different answers, in some sense it tells you you're doing the wrong thing, right?
But when you estimate the tension, you want to know, for instance, let's go to the example. So imagine that, I mean, in this example, it's very clear.
Couldn't someone come up, this is a very contrived distribution, couldn't someone come up with a distribution where your method fails?
Okay, then I suggest you to provide this distribution.
Okay, so you're confident that
I think
distribution where your method...
Of course, I tailor-made this example in order to maximize the effect. Right? But in irregular energy, this is happening. And I've not done anything, I have not tailor-made anything. So I think that we cannot say, okay, the marginalized posteriors cannot be used because no, they provide different information. They provide where is the larger fraction of probability in the parameter space. Okay, so coming again here, okay, you can see that looking at the marginalized posterior, you know that here in this region of alpha you will have the larger fraction of probability, and this is the case because here you have a lot of points that behave perfectly well.
Sorry, maybe we continue this discussion? Okay, thank you very much. So let's take a